Hi there, welcome back to The Logic of Risk, episode 8. If you enjoy this podcast, please hit the like button and share it with anyone you think might be interested. Thank you in advance. Are you ready to dive back into propensities and probabilities? Let's go. In our last episode, which is essential listening if you haven't already, we introduced the propensity school of thought as seen by Peirce and Popper in defining what probability is. Think back to those physics and chemistry experiments we did at school. You would set up an experimental configuration, gathering all the elements needed, verifying conditions like temperature and light, and then following a specific sequence of operations to produce a particular outcome, such as a reaction. The outcome would occur almost every time, but not always, because a slight variation in the setup or a moment of inattention might lead to a different result. Repeating the experiment many times would yield the desired outcome a high percentage of time, suggesting that the experiment had a propensity to produce that result. That's the essence of the propensity idea. Once a random phenomenon is set up and its conditions verified, repeating it over time will yield certain outcomes with varying likelihoods, as if an invisible force were pushing events in particular directions. This force is the propensity, which we cannot observe directly but can approximate through our measurements via probability. This idea that we can't observe the propensity directly but can only infer it from experimental outcomes is not as strange as it might seem. In modern physics, similar concepts appear in discussions of fields, potentials, and wave functions. Philosophically, Popper's notion of propensity has an Aristotelian flavor, evoking the concept of potentiality. In our last episode, we ended by reading an excerpt from a 1959 article by Popper, where he argues that his propensity view is more reconcilable with quantum mechanics than the frequentist approach. More importantly, it is capable of handling single-case phenomena, something that neither von Mises nor Peirce considered feasible. These are, without a doubt, significant innovations. Regarding the compatibility between propensities and quantum mechanics, I will offer a few brief remarks now and promise that we will revisit this topic in detail later, perhaps even with a colleague of mine, a physicist who works with these issues every day. Popper's propensity interpretation lets us view quantum probabilities as real physical tendencies rather than mere reflections of our ignorance. In quantum mechanics, the wave function assigns probabilities to different outcomes, and, according to Popper, these probabilities represent inherent propensities of a system to behave in certain ways when measured. This means that, even if we had complete knowledge of the wave function, the probabilistic nature of the outcomes remains an objective feature of reality. The idea of an objective tendency fits neatly with quantum mechanics. The probabilities derived from the wave function are not just abstract statistical frequencies or subjective beliefs. They are physical dispositions built into the experimental setup itself. This interpretation also reinforces the notion that measurement and reality in the quantum world are deeply intertwined. The randomness we observe in quantum measurements isn't merely a result of incomplete information, it is a fundamental aspect of nature, suggesting that indeterminacy is intrinsic to the system. Context dependence is another central idea in both quantum mechanics and Popper's view. In quantum experiments, the results can vary dramatically depending on the specific conditions under which a measurement is made, such as the arrangement of detectors, the orientation of the measuring devices, or other aspects of the setup. This contextuality means that the properties we observe emerge not just from the system itself, but from its interaction with the measurement apparatus. Similarly, in Popper's framework, the propensities are tied to these experimental contexts. Different setups will naturally yield different probability distributions, reflecting the influence of context on the outcome. Furthermore, in quantum mechanics, concepts like interference and superposition illustrate the complexity of the quantum behavior. Superposition refers to the ability of a quantum system to exist in a combination of multiple states simultaneously. Until a measurement is made, a particle can be in a state that is a linear combination of several possible outcomes. Interference occurs when the probability amplitudes of these superposed states combine, sometimes reinforcing each other, constructive interference, or canceling each other out, destructive interference. This interplay of amplitudes can lead to surprising results that challenge our classical intuitions about probability. Some scholars, like Professor Leslie Ballantyne, argue that the propensity approach could provide a way to understand these phenomena, though that discussion ventures into highly technical territory. In essence, Popper's view helps us see quantum probabilities not as simple ratios or mere expressions of ignorance, but as real context-dependent properties of the physical world. This perspective captures the heart of quantum uncertainty and the intricate dance of superposition and interference, where a system's full spectrum of propensities interacts in a manner deeply influenced by its experimental context. Popper also points out that his propensity view converges with the frequentist approach when it comes to large-scale random events. For a mass phenomenon, a collective, as von Mises would say, the probability of an event is simply the limit toward which the relative frequency converges over an arbitrarily large number of independent repetitions of the experiment. The difference is mainly formal. For the propensionist, the limit of the relative frequency reflects an underlying tendency, a propensity of the phenomenon to generate certain outcomes. In the end, the propensity idea is essentially an attempt to physicalize probability. When it comes to large-scale phenomena, the criticisms of viewing probability as propensity are similar to those aimed at frequentism. Everything works well as long as we have high-quality, abundant data, and we are not dealing with extremely volatile phenomena characterized by tail events, that is, rare extreme outcomes with significant impact. However, Popper's propensity view departs from frequentism when dealing with single-case one-shot events. According to Popper, the propensity view can assign a probability to a single event if three conditions are met. First, we consider the one-shot phenomenon as representative of a sequence, a potential collective, that is not yet actual, but is virtually conceivable. Second, this imaginary sequence is composed of events based on precise, carefully analyzed surrounding conditions. Third, the virtual sequence, and hence the probability of the event, can be conceived as resulting from some hidden propensity. All in all, Popper's idea is similar to thought experiments like the Einstein-Podolsky-Rosen paradox or Schrödinger's cat, where a carefully described experimental setup is imagined and analyzed through the laws of physics rather than direct data collection. For example, if I want to estimate the probability of a terrorist attack, I can imagine the event, assess the surrounding conditions, security measures, infrastructure, the capabilities of the group, and mentally replicate the experiment across various scenarios. Thus, for one-shot events, probability is not the limit of relative frequency over many repetitions, but rather a conjecture based on our knowledge of the phenomenon's conditions. According to Popper, this conjecture becomes verifiable if we can produce a kind of sample of the virtual sequence, even if only in an analogous, scaled-down experimental form or via computer simulations. Yet, one must ask, on what objective elements does the propensity theory base its formulation of objective probability values for a single event? After all, if relative frequencies can only be defined in terms of a virtual sequence of phenomena, how can we ensure objectivity in the single case scenario? One answer could be the propensionist relies on available empirical evidence and the observed conditions of the event at hand without resorting to personal biases. But even selecting the relevant empirical evidence can allow room for subjective modification. Nothing guarantees that two evaluators will consider the same conditions equally important. While thought experiments and contextualization can in theory support a propensity-based approach, in practice it is challenging to guarantee the objectivity that relative frequencies provide for large-scale phenomena. Some propensionists propose contextualization operations, ensuring that the evaluator is fully informed about the history and dynamics of the conditions underlying the phenomenon. Rather than a single snapshot, we need the full movie to build a robust probability assertion. This method draws on historical and historiographical techniques to reconstruct data, episodes, and sequences leading to a specific event. In my view, while contextualization is an interesting idea, it doesn't entirely resolve the inherent subjectivity in conjecturing about single events. Relative frequencies offer an impression of objectivity for collectives, but for single cases, subjective judgments are difficult to avoid. Ultimately, even subjectivists might agree with Popper's use of thought experiments and contextualization, acknowledging that these are subjective solutions, though we might say so softly lest we disturb Popper's legacy. As we will see shortly, the subjectivist view turns out to be the only one that is internally consistent for single-case phenomena. You may or may not favor that approach, but its coherence is undeniable. So, why all this discussion on propensities? It isn't just a philosophical mathematical diversion. The ideas of Peirce and Popper have led to important studies and developments. I recommend Donald Gillies' work, An Objective Theory of Probability. In it, Gillies leans more toward Peirce than Popper, and even introduces his own version of a propensity theory, though he doesn't call it that. In his paper Varieties of Propensity, Gillies explores different interpretations of propensity theory and classifies them into two main categories: long-run propensity theories and single-case propensity theories. The long-run perspective asserts that probabilities emerge from repeated conditions observable through frequencies that approximate theoretical values. In contrast, single-case theories propose that probabilities can be meaningful even for one-off events, treating them as intrinsic properties of individual occurrences. This latter view, championed by figures such as Popper, Miller, and Fetzer, aims to preserve the notion of objective probabilities, even when events cannot be repeated. A central difficulty for single-case theories is the reference class problem. The probability of an event often depends on how it is categorized, whether as part of a broad population or a more specific subgroup. For example, the probability that a particular 40-year-old man will live to 41 may vary depending on whether he is considered as just a 40-year-old, as an Englishman, or as a smoker. This variability complicates the idea of a single objective probability for an individual event. Gillies suggests that while subjective probabilities may be based on objective data, they remain ultimately unavoidable in such cases. Another major challenge is Humphrey's paradox, which highlights an asymmetry between probability and causality. While probabilities allow for bidirectional reasoning, computing the probability of an effect given a cause and vice versa, causal relationships are directional, with the cause preceding its effect. This discrepancy creates difficulties for propensity theories that attempt to treat probabilities purely as causal tendencies. For example, it seems nonsensical to say that a corpse had a propensity to have been shot, even though we might compute the probability of death by gunshot if the cause were known. Gillies ultimately defends a long-run propensity interpretation. By linking probabilities to repeated conditions rather than single instances, this approach remains scientifically testable and avoids the pitfalls of single-case theories. He criticizes later versions of Popper's approach for turning propensities into properties of entire states of the universe, making them more metaphysical than empirical. Before we close this episode, let's return briefly to the reference class problem, a crucial issue for both frequentism and risk management. This problem is about choosing the right reference class when estimating a probability. For instance, if you are estimating the probability of a highway accident, should you use data from one highway, all Italian highways, or even all European highways? And within that, should you consider only cars or also motorcycles and trucks? Over what time period should these conditions be considered? Changes in technology, habits, and traffic rules all influence which reference class is appropriate. Although describing the problem is straightforward, solving it is notoriously difficult. In fact, many media polls falter because they fail to define their reference class properly. Sometimes, defining the reference class can resolve the distinction between large-scale phenomena and single-case events. For example, I might ask about the probability of a specific car, identified by its license plate, getting into an accident. That's a single-case phenomenon and difficult to manage with current approaches. However, by dropping the license plate requirement and considering all similar cars, I can build an initial collective that lends itself to analysis. Of course, not every situation allows for such grouping, and some phenomena are truly one-shot. The reference class problem is deeply intertwined with the statistical syllogism that will become a cornerstone of our risk management approach. That wraps up episode 8. We still have a few more episodes ahead on the definitions of probability. We will discuss logicism, the axiomatic view, and the subjectivist perspective before moving on to risk measures and their applications. That's all for now. Until next time, when we will discover that probability does not exist. Ciao ciao!